Hey everyone, this is Cam from Odell. We're going to get started here with Neil Holden from Krueger. Neil's been with Krueger since about 2008, and he's the specialty product manager. He'll be talking to you about displacement ventilation. Just a few housekeeping things before we get started here. There is a chat bubble over to the right-hand side of your screen, as well as somewhere to ask questions. We're going to get to the questions near the end of the webinar. So if you have any questions while we're going through, just reference what Neil was talking about and put your questions in there. And then if there is something that you'd like to talk about urgently, there's an option to raise your hand. So if you do that, then we can know that you want to get to that right away. Probably just give it another minute or two just to, we've got a few stragglers it looks like, so we'll get started here just a sec. All right, the numbers seem to have stabilized. So Neil, you can take it away there.
Thank you, Cam. So thank you for joining me today, everybody. So we're going to talk a little bit about displacement ventilation. Displacement ventilation is kind of a unique type of air distribution method. At Krueger, we classify it as a specialty product. So it kind of falls under my wheelhouse. I manage the specialty products. So displacement is a really cool type of product, and depending on the application that you're working with, it may make a lot of sense to help overcome some obstacles that traditional overhead mixing can encounter. So let's just jump right into it. All right, so here in the slide here, we see kind of a sliced view, elevation view of a typical displacement type of setup. And so you can see on the image to the left, there is a displacement unit that's in the bottom left-hand corner of that image, and it's up against the wall. And typically, we're going to focus on placing displacement in these type of perimeter locations because that's located in the adjacent zone. So the adjacent zone is defined by ASHRAE. It's about 3 feet away from the outer walls. And so that kind of provides us an already existing kind of space away from the wall that we can introduce air, and we know that occupants aren't going to be placed directly in that adjacent zone. So we basically have kind of a buffer region running around the perimeter of a zone or a room where we can place our displacement products. And we'll talk a little bit more about why that adjacent zone is important a little bit later in this presentation. But before we get to that, let's go over some of the elements in these illustrations. So we see a displacement product put in the bottom left-hand corner, and we see it discharging cool air. And as that cool air leaves the face of the displacement unit, it falls towards the ground. It's introduced at a very low velocity. So the cool air just collects on the ground. It almost spills out almost like a fluid. And then it will start inching its way into the room towards the occupants. So in this example, we have 2 warm bodies that are in the occupied zone. So those 2 occupants, they're actually giving off a natural heat plume that rises off their body at about a velocity of about 30 to 35 feet per minute. So that heat plume and that discharge velocity is all that it takes to pull that cool air towards those warm bodies. So as that cool air falls towards the floor, it's going to start inching into the room and seek out the warm areas in the occupied zone. So in this case, it's going to be occupants or any equipment that might be giving off warm discharge. As that cool air encounters that warm body, it's going to crawl up that entity and actually exhaust itself upwards towards the ceiling. So in this illustration right here, towards the ceiling, we have what we've called the upper mix zone. And then we have a return grill in the very top of that upper mix zone. So what we've created here is we've created a supply at a location that is directly at floor level. And then we have our return at the top of the ceiling. So we're creating what's essentially a one-pass ventilation system. We're introducing cool air at the floor, introducing it into the room. It's seeking out the warm occupants, cooling those occupants, and as that cool air warms, it in itself rises up into the upper mix zone where it's then exhausted out of the return grill. Now, some advantages of this one pass type of discharge pattern are that it helps improve the indoor air quality. And the way that it does that is if we look at the images on the left side of the slide, you'll see at the bottom, there's a traditional mixing overhead air distribution. So this is kind of what we're accustomed to. You have a diffuser in a ceiling that's discharging air at a relatively high velocity directly at the ceiling and discharging it along the ceiling through the Quandt effect until it encounters a wall vertical surface that it will entrain upon and ride down. So what we see in this space is where the occupants are, we see all these dots, and these dots are the particulates, or the stuff that we're actually trying to ventilate out of the space and ideally keep the room air clean. So the fully mixed air distribution actually swirls these particulates around, and because since our return grill is in the ceiling, that air does not easily exhaust out of the space. However, on the displacement application side, since we are creating a one pass, the cool air discharges at the floor, it seeks out the warm bodies, and as that cool air warms, it will rise up, and as it's rising up and ventilating out of the space, it'll take some of those particulates with it. So this is one of the main ways that displacement actually helps to improve indoor air quality compared to a fully mixed air distribution using traditional overhead diffusers. So that's just one advantage of using displacement. If we go to the next slide here, we'll see that we're going to define the adjacent zone. So we talked a little bit about the adjacent zone and why it's important and why we place these along the perimeter of a space. And the reason that we do that is we want to take advantage of that adjacent zone that's already predefined by ASHRAE, where you don't have any occupants located. And basically the adjacent zone is the area directly in front of the displacement device that will have slightly perceivable draft conditions. So, and when I say draft conditions, I don't mean that it's going to create comfort issues every time you walk past a displacement device. We actually utilize these in our training room at the Krueger engineering headquarters, and I've spent many meetings leaning up against these for maybe 45 minutes to an hour, and it's perfectly fine. So what we don't want to do though is we don't want to put somebody that's going to be there for 8 hours at a day. So that just means we don't want to place permanent occupants, desks, permanent seating arrangements that are going to occupy the adjacent zone of the displacement diffuser. So the adjacent zone is just an area measured in feet around the face of the displacement device where we don't want to put occupants for an extended period of time. And anytime you're sizing a displacement unit, it's going to have performance data that you're referring to, and this performance data should have the adjacent zone of that particular diffuser referenced based on the amount of CFM that it's going to be providing. So beyond the adjacent zone, let's look at some of the typical performance of a displacement product. So we're sticking with the unit that's mounted in a low sidewall type of application. And here we see it providing isothermal air. So the supply air is the same temperature as the room air. And in that configuration, the air is just going to discharge and just continue on a straight path. It's just blowing straight in the room. It's not rising, it's not falling, there's no buoyancy. However, in cooling, which is the main mode that the displacement operates under, you'll see that the cool air is cooler than the room air. There's a delta T, and so the cool air tends to fall towards the floor or spill out onto the floor. However, in heating, displacement does not work quite as well because of the buoyancy forces that take effect on that warm air. Since we're discharging the warm air at a lower velocity, it tends to head towards the ceiling like a hot air balloon rather quickly. So heating out of a displacement device isn't exactly ideal. However, Displacement is still perfectly suitable for many applications on the interior zones where primarily you're going to be concerned with is cooling only. That example I mentioned earlier, where we utilize some of these in our training room, that training room is in the interior zone of a building. And so we actually don't have to worry about supplying heat to it throughout most of the year. So really that room, the training room, is supplied by displacement units alone, and it's only supplied in cooling mode. On the perimeter of your building, you're still going to need to provide some type of heat solution. So that could be linear slots along the ceiling, along the glass. But on the interior zones, displacement and cooling only is still a very viable solution. So let's talk about some of the discharge patterns and about how far you can treat a space with a displacement unit. The rule of thumb is one displacement unit has a reach of up to a maximum of about 30 feet. And so you can see in this image at the top, we have a supply displacement unit on the left side of the wall, and you can see this discharge reaching up to 30 feet. Now, if you have a space that's larger than 30 feet, then you need to start thinking about installing multiple displacement DV locations. So in this example, we have a space that's up to 60 feet wide, and you just split the DV units to either side of the wall. And so they'll reach up to a maximum of 60 feet because each one is handling about 30 feet. So one of the unique things about displacement is we really don't deal with throw distances. You know, throw distance is something that we're very accustomed to when working with grills, registers, and diffusers. However, with displacement, since we're not discharging at high velocities, we're basically using physics and thermodynamics for that cool air to creep along the floor and seek out the warm bodies in the zone. And so that air will tend to head towards wherever those warm bodies are located. So you don't have to concern yourself as much with throw values. In fact, when you look at displacement performance data, there really is no throw value. You can use our selection software, which I'm going to discuss and show some examples of at the end of this presentation, to determine exactly how far it will throw and reach at a maximum based on the CFM you're providing. But the rule of thumb is typically you can service an area up to a 30-foot maximum with a single displacement unit. Now let's watch a little smoke video that demonstrates kind of how that cool air can be introduced into a space. And we have a warm heat source placed in the middle of this room. So I want you to see how that cool air seeks out that heat and then actually rises up that heat source and ventilates up towards the ceiling. So for our heat source in this demonstration, we're using a light bulb. And I take no ownership of the music that was chosen for this video. So these are AHBs. These are column style displacement diffusers. And so this video was taken from our test lab. My goodness. I'm just gonna go ahead and mute that. So our heat source is right in the middle. And so right now what you see is the discharge. Let me keep that playing. And so right now you can't see anything, but if you keep focusing on that heat source in the middle of the room, now you can start to see some of that displacement cool air being exhausted up towards that heat. So our heat plume is our cold air is seeking out that heat source, rising up, and then ventilating back up towards the ceiling. So this is that true one-pass system that DV ventilation can bring that is actually more effective for ventilating a space than traditional overhead. So I'm going to play that just one more time so we can kind of focus in a little bit more early on the heat source. So we have our cool air just falling down to the floor from the AHBs. The air temperature is about 64 degrees. Our room temperature at this moment is about 70, and we're discharging about 400 CFM through the AFBs total. So again, you can see the smoke helping to illustrate how the air is discharging up towards the ceiling. And our ceiling is where our return grills are located. So we're exhausting the air from the floor all the way up to the ceiling. And as that air is exhausted, it's taking some of those nasties with it. And that's one of the reasons that displacement is really recommended for certain unique applications, even industrial applications. Welding, for example, is a unique application where displacement is advantageous because it does help to effectively ventilate the space more effectively. So it'll carry some of those fumes and that smokiness out of the way more effectively than a traditional overhead introduction of high mixing air would. So some of this applications where displacement systems would work better than traditional overhead is if your supply air is cooler than the room air. So essentially, if it's a primarily cooling application. Also, if the contaminants are warmer and or lighter than the room air. So that example I mentioned of a welding bay, that would be an example where the contaminants are warmer and or lighter than the room air. If the room height is 9 feet or more. So this is an important one because a lot of times when you have really tall ceilings, traditional overhead can become a challenge, especially the taller the ceiling, the more difficult it's going to be. Since displacement is introducing air directly at the occupied level, you really eliminate all of those high ceiling challenges that you would encounter with traditional overhead mixing. And we'll go over some examples later in the presentation that show exactly how that's advantageous for some very large structures. Also, low noise levels. So displacement, we're discharging at a lower velocity. So the noise levels coming out of displacement devices are typically in between 20 to 25 NC. So this is one of the reasons that schools are very, very interested in the displacement applications. A lot of the orders that we see are specifically for schools. A lot of schools have done studies that show that displacement can actually improve test scores in the entire school. So when I first read that, I thought it was a little bit of a stretch, but it comes down to the core concepts of improved air quality. And so improved air quality, you have lower noise levels, so it's easier for students to pay attention. You have fewer contaminants in the air because it's more effective at ventilating the space. So theoretically, there should be fewer sick days taken by students and teachers. So there's more learning because there's more attendance. And also, since you're introducing the air at a lower velocity, there's lower risk of draft and comfort issues. So if students are at a level of comfort, it's easier for them to pay attention. So it came down to those three concepts, but yeah, that was an actual study done that shows that the schools that implement displacement tend to have higher test scores after those products have been installed. So it's I thought that was interesting and just wanted to share that. But let's talk about some additional advantages of displacement. And some of the really important ones to focus on are the energy savings potential. So the key word there is potential, because it always comes down to the job, the specific equipment that they're utilizing. But theoretically, displacement, since you're pushing the air at a lower velocity, you could use smaller fans. Smaller fans means less equipment, less expensive equipment, and lower RPM, so that equipment should have a longer lifespan. Also, our target discharge temp for displacement is about 61 to 70 degrees Fahrenheit, which is warmer than traditional overhead. So warmer air supply equals a greater chiller efficiency. Your chiller doesn't have to work quite as hard. Also, high ventilation effectiveness. ASHRAE actually determined that displacement provides a higher ventilation rate than overhead by about 20%. So your ventilation effectiveness score is 1.2. That means theoretically you can supply 20% less air and still ventilate the space as effectively as an overhead traditional mixing system. So what that translates to is you can use displacement and supply less amount of air. So again, that kind of circles back to smaller fans. And one we already touched on is the better indoor air quality in the occupied zone. And so that provides benefits that are pretty much self-explanatory. Better indoor air quality means better air quality, which means better comfort for the occupants in the space. Here are some of the Krueger displacement models that we provide. And one of the things I love about displacement is that it's super simple in its concepts. It's basically, I'm taking lower velocity air that's slightly warmer, and I'm just introducing it right where the people are. So I'm just taking the standard overhead and just flipping it on its head. So now the stuff that's in the ceiling, the supply that's typically in the ceiling is going to be on the floor. Now, once you get beyond that, the only distinction between one displacement product to the next is its shape. A lot of the displacement products are focused on aesthetics since they are in the occupied zone and they are going to be visible by the occupants. So we give a variety of shapes and structures to help integrate into the space and make it as seamless as possible, and even perhaps add to the architectural aesthetics of that space. So here you can see on this sheet various shapes and flavors of the displacement models that we saw. Here's the AFB, which was shown in that demo video in the with that really super awesome music. But really, we have many shapes to choose from. The AFC is a 360-degree round shape, so it could be used on applications where you may not have a wall structure. So if you have a really large space, then you actually will have to address displacement by a freestanding displacement that has a duct coming from above or maybe down below in the floor. And we'll show some examples of that later in the slideshow. And we also have an AFD, which is a wall-mounted unit. It's kind of a two-way angular. AFE is one of the most popular. This mounts inside the wall. So this allows it to actually kind of integrate a little bit more seamlessly in the space. This includes its own 4-inch plenum. So this would be installed in your space, and the 4-inch plenum allows that to fit between your studs, and then you can just connect to the duct coming down from the ceiling. AFF is a 3-sided unit with rounded corners. The AFH, this is a somewhat new unit that we're preparing to launch in the next few months. This kind of is a ceiling mounting unit, and it is a changeover heating and cooling ceiling discharge unit. So we're taking one of the aspects that displacement doesn't do well with and finding a way to integrate heating and make it effective. And the way that we do that is when it's in cooling mode, it discharges its air through a perforated face. And then in heating mode, we have a damper structure that switches over to force the air through a linear slot. So your warm air is discharging at a high velocity, as it would in a traditional overhead. But in cooling, it switches over to a perf face that slows it down because it has a low free area. So this is kind of the best of the both worlds, and this should be launching within the next few weeks under the name AFH. So right now it's up in the ceiling of our lab being tested, and that's going to be launching out pretty soon. So we'll be excited to launch that and get the word out to everybody about a new exciting product that kind of overcomes one of the big limitations of displacement in regard to heating. AFP is a 180-degree round face. AFQ is a 90-degree. You can get it in a round or flat face configuration. And then finally, we have the AFR, which is similar to the AFE, except the AFR does not include its own plenum. The AFR just includes mounting rails, which would mount into the hole opening, and then you can snap this perf face to the mounting rails. So the mounting rails have some spring clips that it uses to engage the mounting rails. So, and the AFR would be installed into a opening that kind of has its own plenum created behind it. The AFR is similar to the AFE, except it doesn't have any flange. So it's even more non-invasive than the AFE, and it's actually one of the more preferred models from the architects. All right, so some applications that displacement works well for include smoking lounge. So this is just a good example where you have particulates in a space that you're trying to ventilate. Also kitchen, you have a lot of warm discharge air that you're trying to get out of the space. So displacement will work well for that, for getting that warm, hot air out of the kitchen space up towards the ceiling. Restaurants, auditoriums, atriums, gyms, and more. And one of the common themes that you see between these is that they have somewhat open floor concepts. So large spaces where you have not a lot of walls or structures that are going to be blocking the airflow are perfect for displacement. So lobbies, foyers, um, any large waiting space is perfect for displacement. So here's an example of how you would duct through the floor and utilize displacement in a very large high ceiling structure. So here it would be difficult to use traditional overhead HVAC due to the height of the ceiling. So we've introduced displacement and ducted it through the floor. So you don't have any ducts coming down from the ceiling. You basically have ducts penetrating the floor, and then the displacement product is mounted directly to that duct. And why this works so well is because you're introducing your cool air towards the floor, and it's going to naturally rise up and exhaust out towards the ceiling space. So here's Heathrow Airport in London, and they have some 360-degree round AFC devices, and they have custom tops that I just call them the lipstick top. And the reason that they have these is just it dissuades people from sitting on top of the units and putting anything on top of them. These particular units are made out of stainless steel, so they are very robust. But this work great for this space because it is an open floor space. You have glass walls, which would make it very difficult to introduce air through that surface, and you have a high ceiling. So this type of application is a good candidate for displacement just because of all those reasons I just mentioned. So if you want to duct through the ceiling, it's much the same thing, except you're just going to be running your duct from above. And that's a common application. And we have some examples here showing AFCs. Again, that's a 360-degree round displacement unit. And we have an open floor concept where we have a lot of occupants that are going to be passing through the space. And so we don't have any walls or structures that allow us to conveniently introduce air into the space. So we've actually have some freestanding displacement units which are ducted from the ceiling. And the architect has done a great job of concealing the ducts in the columns. So the ductwork is actually part of the architectural structure in this photograph. In displacement, and you'll notice that there are some chairs and tables that are placed very close to the displacement diffusers, but since this is kind of a cafeteria lunchroom type of space, we don't anticipate people sitting here for more than 2-3 hours at a time. So we're not concerned with the adjacent zones creating a problem. If somebody were sitting here for 8 hours at a time, that might be a problem, but this is somewhat of a transient space. Here's some more AFBs. These are the column style diffusers, and again, they are ducted from above. In this example, they actually purchased them with the duct cover, which is an option that we can provide. It's a sheet metal enclosure that just hides the aesthetics of the raw duct coming down to the displacement product. So here we have the column diffuser on both sides, and then we're concealing the duct with our duct cover option. And the duct cover is an option that's available on all the models that are going to be freestanding. Here again, we have some more column style displacement diffusers. I like this photograph because they did a really good job of integrating the feature of this displacement in the architecture of the building itself. It actually looks like it's supposed to be there. And that's one of the unique things with displacement is that it becomes part of the building structure and the aesthetics of the space. And again, we're ducting from above in this example. So we have a large open space, which is perfect for displacement, so that air would just spill down on the floor and kind of seek out any warm bodies that walk through or are currently occupied in that space. Here's a great example of displacement. This is Bangkok Airport, and we have these blade style displacement diffusers that discharge on both sides. And so we have a very, very large high ceiling space, glass walls. So introducing air from the glass wall would be very difficult. Introducing air from the ceiling would be very difficult. So displacement for this type of application is actually ideal over traditional overhead because we're introducing the air right at the occupied space. And so what that allows us to do is we're only treating the occupied space We're not going to waste a bunch of energy trying to treat the ceiling space, get the air down to the occupied space, fight all that distance, fight all that delta T. We're just going to introduce our 61 to 70 degree air right at the occupied zone where it's needed. And that's again where some of the energy savings potential of displacement products come into play. So again, this is somewhat of a transient space. So we have people coming and going, but hopefully they're able to make their flights and not having to spend a night at the airport, so we don't have to worry about adjacent zone issues in this application. This is a unique application. I just wanted to include this one because it shows something that you can do with the displacement that you can't do with overhead. And that is actually, in this example, they're painting the face of some AHBs to kind of help integrate it with the architectural style of the space and the overall theme. And this is a Southwestern style restaurant. So they serve New Mexican cuisine. So what better way than to actually, paint some Santa Fe type of Southwestern Native American designs on diffusers themselves. So that's something that unique that you can do with displacement that you can't really do with traditional overhead. That is just an option that if an architect wants to get creative, then displacement gives them some new options. Here we have a smoking room, and this was in JFK Airport. I don't know if this is actually still there since smoking rooms are becoming, going the way of the dodo. But smoking room was the perfect application for displacement because again, we have lightweight contaminants, the smoke, that we want to remove from the occupied space up towards the ceiling. And what better way to do that than with displacement? So we're introducing our cool air at the floor level, right at the occupant zone, and it's going to pass over the occupants, warm, and then exhaust towards the ceiling and take that smoky discharge with it. And you can see in this ceiling, they actually have a lattice structure that's probably going to some air scrubbers that are kind of pulling the air and then recycling it and then pushing it back down to the displacement units again. Okay, so that is the end of the slideshow. And what I'm going to do now is I'm going to jump over to our K-HIT software. So our K-HIT software is available for download on our website. That's Krueger-hvac.com. And so the K-HIT is an excellent tool because it's not only allows you to select and size the units, it also gives you a visual feedback of the performance because it includes isovel patterns, and you can actually place units in a 3D virtual space and see where those isovels from that particular unit are going to go. And you can actually determine what the velocities are going to be in that space. So it just gives you all those warm and fuzzies that whatever you lay out, there's not going to be any issue of occupant comfort in that space. So I'm just going to kind of jump into an example here. And so what we're going to do is we're going to go to our product search. And we have a few different products in here because K-HIT is also used for chilled beam selection. But we're going to focus on the low velocity units. That's what we call our displacement units. And you can see the models that we have readily available to choose from here. So what I'm going to do is I'm going to choose an AFQ. It's a corner unit. So here, and the AFQ, what we see here is some information about the AFQ, but there's also various tabs over here that essentially contain all the information on that product. Here's a 3D view of the AFQ, so you can kind of spin it around, see what it looks like. Basically, these serve as all the submittal information for the product. Material, accessories, function, installation, surfacing, specification, additional documents about IOM if you want to download the IOM, product spec code, and of course, performance. So now we're going to talk a little bit about the performance. So what I'm going to do is, if I can get this menu out of the way, first I'm going to select a size, and I'm just going to pick a mid-size unit, that's 16 by 47 with a 10-inch duct. And I'm going to add that to my project. And there's really nothing to select on these units other than size, because there's not a whole lot of options. So I say, okay, then I go to performance and I click on cooling flow pattern. And here we can see our 3D space and actually the AFQ set in a corner, and those little blue dots are the isovel, the discharge pattern coming from the unit. So this is nice, and the ghosted dashed region inside the box, that's our occupied zone. So that'll actually help us visualize what that isovel is doing when it starts to penetrate into the occupied zone. So, and we can customize the size of this room. I'll show you how to do that right now. Go to design data. And so here we can see how much CFM we're supplying through the unit. Their supplier temp. I'm going to set this to about 60 degrees. So your target supplier temp for your displacement unit needs to be about 10 to 12 degrees of what your ambient target temp for the room is. So if I were to say shoot for 72 degrees in the room, I would probably need to supply 60 to 62 degrees of cool air. So I'm going to set this to 60 degrees right now. I'm going to leave the CFM where it is. Typically for your floor, a nice rule of thumb for supplier to floor area is about half a CFM to 2 CFM per square foot of floor space. So here we can see a few little details about the performance of the unit. There's our pressure drop, and here's our noise level. So right now we're sitting at 11 NC. So that's basically almost inaudible, which is great. So here we see our design view or ISO view, but let's take a look at it from maybe the side, and we can actually use this box to adjust the isovel terminal velocity. So if I want to see how far the isovels go, if I set this to 30 feet per minute, it's going to show us the isovels penetrating a little bit farther. And I've also set it to a side view, and so I'm going to zoom in here. And what we see is we can see this discharging into the space, and it starts to collapse rather quickly when it penetrates into the occupied zone, and then it collapses down to just about an inch or two above the floor level. And that's what you can see by this little thin blue dash line. So that's kind of what you want it to do. In fact, if I wanted to, I could probably scale back the CFM a little bit more. But as far as is this device going to be able to service this room? The answer is yes, because if you remember, our rule of thumb is you can go up to about 30 feet, and this room is 24 feet wide. So this unit by itself would be perfectly fine for an office of maybe 1 or 2 people. And so what I'm going to do now is I'm going to place another unit in the space. So here I can see my layout. This red triangle here is my current AFQ. So I'm going to add, let's see here. Let's see. Can move it around a little bit. I'll tell you what, I have to actually go back to my selected products. Actually, my engineering selected products here. And I'm going to change the quantity to 4. Okay. There we go. So now I'm introducing some additional units here, and I'm going to go up to 4. And you can see I'm just selecting these location, stepping through the locations. So K-hit, since this is a corner unit, it kind of knows like, hey, this has to go in a corner. So it's kind of selecting the different corner locations and orientations. So you just kind of move this around until you get to the layout that you prefer. So I'm going to go with one in every corner just to see what that does. And you'll notice I've adjusted my total airflow. So that is divided through all the units. So this is 400 CFM, but each unit is only going to have 100 CFM. And you can see right here, it's telling me like, hey, that's way too low of air. So it's saying that for 4 devices at this size, you need at least 848 CFM. So I'll just put 850 here. And so now it's like, oh, okay, that's better. Here's your 11 NC for, says design status, okay. So let's just take a look at that. So we've added 4, that's way overkill. We didn't need 4, we really only needed 1 for this size of room, for the amount of air that we were providing. So this is just kind of showing you how you can play around with the layouts. Now, if we go and take a look at a different displacement unit, let's take a look at the AFE, which is the in-wall style diffuser. And the most common size of that is just kind of a 2x4. So we'll just add that to the project. And I'm just gonna put in 2. All right. Now I go to cooling flow pattern, and already it's saying it doesn't like something. So I got to go over here. Oh, it's trying to force 850 CFM through this one AFE. So no, it's saying that can take a maximum of 423. So I'm just going to reduce this to like 250, and our NC is 26. So I can tell you right now, based on that NC, that we have too much air, because really it's a little higher. So I'm gonna just step that down to 200, because yeah, NC of 19, that's much quieter. Set that to 60. And again, if you want to increase the number and play around with orientation, you're going to be working in this space right here. So now we have the addition of columns and rows. Since this isn't a corner unit, we have a little bit more freedom to position these. So columns will be introducing additional units like this. However, that one is free standing in free space, and these are AFEs that need to be mounted on walls. So we probably won't go with that orientation. We'd go with something similar to this. And if I wanted to add more, I could do something like this. And really, I can just make a whole wall of AFEs. Of course, it's saying I need more air, so let's go to 1400. So here is my room filled with AFEs. And this is, again, way, way, way overkill. We see our isobel is just covering everything. So for this amount of space, let's figure out how much air we would actually need. So like I was saying earlier, we want to size the amount of air for about 0.4 CFM to 2 CFM per square foot. So I'm just going to do 1 CFM per square foot. So we have a room that's 20 by 24, so 480. So I'm going to shoot for 480 CFM total to provide ventilation in this room. So I'm going to back out and go to my design data one more time. And I'm going to say I want 480 CFM of air. And it's telling me, well, you have way too many because you need at least this much air for these numbers. So I'm going to just step these down. Whoops. Let's go with 1. Let's see. So at 480 CFM, I still have an NC of 25. So that's still a little much. So I'm going to add 1 more. And now we have an NC of 11. So either you can stop at 2 or you could just increase it to 3. It just kind of depends on what NC level you want to target for your space. But if we leave it at 2 or if we set it to 3, we're still providing the right amount of air based on a square footage using displacement for this space. So I'm just going to leave it at 2 and flip to the other side. Rows 1. There we go. So let's get a side view of that. And I'm going to reduce the velocity to 49 feet per minute. All right. So we kind of see here that we have them discharging on opposite sides. The discharge pattern is pretty much collapsing when it hits the occupied zone. So by the time it gets to the occupied zone, it's down on the floor. So we're not worried about drafts. And so if I had a desk, you know, a couple of desks in this space, I would say that would be a perfectly suitable application and layout using displacement. If you wanted to get even more specific, then you could always move these. So if I take my cursor and click on the wall here, actually it's giving me the distance between the wall and this location of the diffuser. So if I wanted this right up against the wall, I'll just go 12 inches. And so now it's shoving these all the way over to the corner. So that might be one way that you can help further avoid any potential for draft issues. So let's take a look at that now. So now if, we see it's discharging over here, but again, since the distance from the wall is less than 30 feet, even if I had a desk all the way over here, this air is still going to creep across the floor and seek out that warm body in the space. All right, so that's pretty much the ins and out of K-Hit. Like I said, K-Hit is available for download from our website. So let me just go back to our website. So if you want to access K-Hit, you can log on to our website, krueger-hvac.com, and then mouse over software and click on K-Hit selection. And then there's going to be the green download link right on the right side of the screen right there. All right. So at this time, I was just going to touch on the basic design parameters and then open it up to any questions from the attendees. So just to recap, the summary is that displacement is a great solution for specific applications that may be a challenge to address with traditional overhead. So if you have a high ceiling, like above 10 feet, then displacement is a good candidate. If you have an application that needs primarily cooling, of course, displacement is a good application. If you have an application where you need to effectively ventilate nasty particulates from a space, then displacement is an appropriate application. And whenever we're trying to provide our air out of the displacement, the rule of thumb is that our supply air temp needs to be about 10 to 12 degrees cooler than our room set point. So again, if we're trying to get a room to cool down to 72 degrees, then our supply discharge needs to be about 60 to 62 degrees coming out of the displacement unit. Also, the velocity coming out of the displacement unit needs to be on a lower side. So typically we recommend shooting for 40 feet per minute discharge velocity out of the face. You don't want your discharge velocity too high, or else you're gonna, run into those draft issues that basically displacement is trying to avoid. So you want your discharge velocity to be around 40. You can be a little high, you can be a little less, but you just don't want to start getting up to 100 feet per minute, because that's basically, the world of high mixing. You want to provide enough supply air to handle at least 0.4 to 2 CFM per square foot of floor space. And your cooling capacity for displacement ranges from about 2 to 8 watts per square foot of floor space. So if you have an application that has cooling capacities that fall within that range, then displacement is an appropriate choice. And again, it comes down to just options of shape, size. There's not a whole lot of configuration that goes on in these products, because essentially they're just big perf diffusers. So now I want to open it up to any questions, or if anybody wants me to add any clarification to anything that we already discussed, I'm open to any questions.
Thanks, Neil. So we do have some questions here. I'll start with the first one. Would this be a recommended method to ventilate a commercial kitchen? I know you touched on this a little bit, but maybe you can speak more to the strategy.
Yes, it would be perfectly fine for ventilating commercial space. So commercial kitchens and even factories are a common application for displacement. For those type of setups, we would recommend providing the supply from the floor level, because you want to introduce that cool air. Typically in kitchens, you're going to have issues with stratification. So displacement is an effective solution when you want to kind of push some of that air out towards the exhaust. So, I mean, with displacement, stratification is occurring. We're just trying to push that warmer, nasty air up towards the stratified zone. So we want the occupied zone to be the nice, comfortable zone. So that's why we're introducing our cool air directly into the adjacent to the occupied zone, So we make sure that we're just treating that space. So it's effective for commercial applications because a lot of times commercial factories have high ceilings, so they want to kind of displace all that stuff that accumulates towards the floor level. Like an example I keep circling back to is there's a lot of welding bays that use displacement, but commercial kitchens are perfect for displacement as well for the same reasons. They're just trying to exhaust different types of nasties out of their space. They have a lot of heat, they have a lot of humidity, and displacement is effective for pushing those out of the occupied zone.
Okay, next question. Where can we see quantitative measures of the better indoor air quality, particularly a comparison graphically or numerically of that versus overhead mixing?
Well, I don't know if I can show you examples, but I can tell you that ASHRAE has assigned displacement a ventilation effectiveness score of 1.2. So since ASHRAE is basically giving us information, we don't really have to put the proof in the pudding because it's basically they're telling us to use this ventilation effectiveness score. So whenever you're using right here, high ventilation effectiveness. So this is just a numeric value, this VE value that ASHRAE has assigned. So basically that is something that we can look up and reference in the knowledge base of all the ASHRAE standards. Now, as far as any kind of a case study or any kind of, I guess, example of proving that out, I don't have anything like that readily available. It's just kind of using the data that ASHRAE is giving us and using the metrics that they're giving us for laying out and determining the effectiveness of the ventilation of those products.
Okay. If displacement is used only for dedicated outside air and cooling and heating are delivered by radiant panel, what are the keys to placement of the radiant panels in relation to the displacement units?
That's a great question. So radiant panels are a good complementary solution for heating to use with displacement. Since radiant doesn't supply any ventilation, all that will be handled by the displacement unit. So as far as locating that in relation to each other, I don't have any real rule of thumb as far as to keep them away from each other or, make sure you place them right here. You definitely can use them together. A lot of radiant panels kind of take up a lot of space in a ceiling. So I guess if you're covering the whole ceiling with radiant panels, then it becomes less of a question of, well, this is just where it has to go. So I think that would be kind of specific to the application, but I don't think there's any specific ramifications, negative ramifications of placing displacement directly next to a radiant panel.
And our last question here, the architect and owner would need to be aware that they need displacement ventilation before the architectural design. Do you find that the owner, in most cases with displacement ventilation, know that that's what they're going to go with prior to the architectural design?
It kind of depends. One of the most common applications for displacement that we've been seeing are specifically a lot of schools. Schools, universities, government jobs, those are the ones that are kind of targeting displacement. And with schools, they're targeting displacement because it's been identified as something that provides specific benefits for their industry. So a lot of times with schools, they start with this from the beginning, or they end up doing a retrofit somewhere down the road. And those go hot and heavy during the summertime, when the school is empty as far as, construction. That's pretty common knowledge. As far as picking it, I think they would have to be very deliberate in picking it early in the process. I think it's something that the architect would have to want at the very beginning. I don't think that the architect would lay something out and then switch it up midstream when somebody suggests displacement. So I think displacement would have to be something that the architect is inherently involved in selection and the okay of using those type of solutions. Because as we know, everything an architect does, they view it as, this is my legacy. So these products are very direct impact on aesthetics. So it's something that the architect would probably need and have a desire to do from the very get-go.
Okay, thanks. And do you have a parameter cheat sheet that we can share with the attendees?
Absolutely. Yes, I can send that over as soon as we're done. I will send that over to you and Nathan, and then we can send that out to anybody who's interested.
Awesome. Thanks a lot, Neil. And to anybody who's listening, if you have any further questions for Neil, you can send them to Nathan or you can send them to myself, and we'll make sure that we forward those on and get you the answers. So thanks a lot for coming.
Cam?
Stay tuned for the next one. Yes.
Sorry, it's Nathan here. There are a couple more questions here. One is, can fire dampers be integrated to the displacement unit where the supply is below floor slab on upper stories?
Say that one more time.
They're looking to know if fire dampers can be integrated into the displacement unit. I'm not sure where you'd use that.
Use what?
Fire dampers?
Fire dampers? Oh. You can actually, when you're coming down in the ductwork, I can't tell you exactly where they need to be located, but since these are in the, these are actual in the room, if you have ductwork coming down, a lot of times they'll locate a measuring station directly at the location of the inlet of the displacement device. So you have the duct coming down, then a measuring station, and then the displacement unit. I have never seen the fire dampers placed directly at the inlet. So you can place them in the ductwork, but I haven't seen anything that's placing them right in the ductwork that's penetrating into that room space. So I have to assume that they're above the ceiling.
Yeah, they're generally at the penetration into the space. So I would think that the fire damper issue would not come down to being able to integrate it into the grill, but rather into the supply duct coming into the space to enter into the grill. So
correct.
If there's further questions on that,
we don't provide.
Somebody's thinking about, we can address that.
Yes, I think that would be something that would have to be, refer to your local codes to see where the appropriate locations of that specific damper would be. But we don't provide any special options for providing the units with a built-in fire damper or really any damper mechanism. Since they're so low flow, a lot of times that any adjustments can be made just directly in the ductwork with any kind of damper device. So we'll provide them with kind of a measuring station that has kind of a butterfly damper if they want, but that's really the only damper option that we provide.
Okay. Yeah, sorry, I think that's one last question here. Is this more expensive to install than the regular system?
Well, that's a great question, and that's really one of the most important questions whenever we're starting this process, is which is going to cost me more upfront. And so I would say that there is a little bit more churn cost, initial cost for displacement, because you do have a little bit longer duct runs. There is more sheet metal involved. These are larger structures. So if you were just to do apples to apples, compare the price of a displacement unit to overhead diffuser, of course, displacement is going to be more expensive. There is a chance that you use fewer displacement products than overhead diffuser locations. So I think this is kind of one of those where we commonly see it's like, yeah, it's a little more upfront, not much more, but there is that potential energy savings where you recoup that cost down the road. So yeah, I think it's kind of like that same analogy of like buying an electric car. It is a little bit more expensive, but there's some energy savings that are more attractive for the long term.
Okay. Well, Neil, again, thank you very much for the presentation, and thank you to all attendees for It's the great questions. And we can certainly follow up with a couple of you that have a few more questions that are follow-ups to some of the other questions we've already answered. So I, again, want to thank everybody for joining us for this session of Isolation Intelligence, and look forward to future webinars that we're putting on. Next one will be held on Wednesday at 3 o'clock, and it's with Plastic Air. We'll be talking about FRP fans and lab hood environments, and sure to be a good one. So thanks, everybody, and we'll talk to you later. Bye.